So when we want to know about a compound, there are three different types of formulas we can have for a chemical compound. And so one type is referred to as the empirical formula. An empirical formula is usually derived from some type of mass analysis. So you have a compound, it uses a particular instrument that determines the amount of each type of element in the formula. And then you can determine the formula of that compound. And the unique thing about empirical formula is that it shows the lowest whole number ratio of moles. So whenever you look at the formula, the common multiple between all the subscripts in the formula should be 1. And majority of ionic compounds are written as empirical formulas. So you'll notice that in all these examples here, KCl, CH4, NO2, they all have a subscript, or the common multiple between the subscripts is 1. And that tells you you have an empirical formula. Now with covalent compounds and a few ionic compounds, but mostly covalent compounds, we can have a molecular formula, which shows you the actual number of atoms of each element in the compound. So here the whole number ratio does not have to be 1, it could be 2, 3, etc. Sometimes for covalent compounds, the molecular formula can be the same as the empirical formula because it has a common multiple of 1. But the majority of the time, you're going to have some type of ratio that's different from 1. So for example, H2O2, common multiple is 2, C6H6, common multiple is 6, C2H4, common multiple is 2. So if you factor out those common multiples, you'll be reduced back down to the empirical formula. And then the structural formula shows you the actual placement of bonds in the atoms of the molecule, and we'll touch more about this in later chapters when we look at what's called Lewis structures. So to give you an example, we'll use hydrogen peroxide. So hydrogen peroxide, the empirical formula is HO. The molecular formula of hydrogen peroxide is H2O2. And the structural formula of hydrogen peroxide looks like this. So that's the difference between all three types of formulas. We look at another example. We look at, say, ethylene, C2H4. The empirical formula is CH2. The molecular formula is C2H4. And the empirical formula looks like this. Again, for the structural formulas, we'll look at more in later chapters when we look at Lewis structures, how to draw these. So that's the difference between all three types of formulas. So next we're going to look at how do we calculate the empirical formula from mass analysis. And then once we determine how to calculate empirical formula, there's just one extra step to calculate the molecular formula. So with the empirical formula, there are three main steps that we do. And the first step, if you're given mass of each element, you just need to use the molar mass to find the moles of each element. So that's always the first step, is that we find the moles of each element. And then once we find the moles of each element, we can divide by the smallest amount to get the ratio of elements to write the formula. So step 1 is we convert mass to moles. Step 2 is we divide by the smallest number of moles to get the ratio. If our ratio is whole numbers, then we can write the formula. Sometimes if you're not given mass of each element, if you're given mass percent, then you assume a 100-gram sample to find mass of each element. So in the problem, if it says we have this percent of carbon, this percent of hydrogen, this percent of oxygen, then what you would do is you would just assume a 100-gram sample, because it's very easy to take a percent of a 100-gram sample, and then you can find the mass of each element and then convert that to moles of each element, then divide by the smallest number to get the ratio, and then check to see if your ratio are whole numbers. If they're not whole numbers, we'll have to do something in order to make them whole numbers. This is the main 3 steps we'll be doing in all of these examples. So here we're determining the empirical formula. We have this compound that was analyzed and found to contain 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. What's the empirical formula? And typically, the order that the elements are given to you is the order that you should write them in the formula. So since it gave us calcium, oxygen, and hydrogen, when we write the formula, we need to put calcium, oxygen, and then hydrogen. So we're given the mass of each element. The first step is to find the moles of each element. And so here, just a little typo, there should be hydrogen here. So now when we find the moles of each element, we divide by the smallest number. In this case, calcium is the smallest, so we divide everything by the moles of calcium. And we get the ratio of elements. Since here they're either exact or pretty close to whole numbers, so we can write the formula as CaO2H2, or more commonly referred to as CaOH2. So again, we take the mass, convert it to moles, find the smallest, or excuse me, divide by the smallest number of moles, and then check the ratios. If they're whole numbers, we can write the formulas. Now we look at another example. So here we have a compound decomposes in a laboratory to produce 24.5 grams of nitrogen and 70 grams of oxygen. Calculate the empirical formula. So again, we're given the mass. So step 1 is to convert mass to moles. And here you would just use the molar mass of nitrogen and oxygen by themselves, not the diatomic molar masses, because we're looking at elemental nitrogen and elemental oxygen, not the diatomic molecules. So you wouldn't use the molar mass of N2 or O2, it's just strictly N and O, because it's analyzing the amount of each element in the compound. So we get our moles of nitrogen and oxygen. We divide by the smallest number of moles, and now you notice that one of them is not a whole number. And if it's 2.5, you can't round to, say, 3 or 2, for example. So the range, you may ask, is, well, how do I know whether to round or not to round? And let's say, you know, for 2, and this is a gray area, but something around approximately maybe, you know, 1.85 to say to approximately maybe 2.1. Even 2.1 is a little bit extreme, but you know, somewhere in this range, it would be okay to round to 2. But you got to be careful, like 2.1, if it's a big molecule, it could be multiplied by 10 to give you a whole number. So this is just a gray area, but somewhere in this range, you know, you could round to 2, for example. But be careful. I mean, the closer it is to 2, the better your chances of rounding is going to be correct. The further away from 2, the more likely maybe it's not 2 and it should be something else. Keep that in mind. But again, this is a gray area not an exact range. So here we have 2.5. So we need to multiply both of the ratios by something to get rid of the 0.5. And in this case, we're going to multiply both of them by 2. And you have to remember to multiply both or all your elements by whatever factor you're using to get rid of the decimal. So a ratio of 1 to 2.5 is the same as a ratio of 2 to 5. And so here, the compound would be N2O5. Now, some other common decimals are things like, for example, 1.25. You would multiply by 4 to give you 5, for example. So quarters are common, even thirds. 1.33 times 3 would be 4. Even 2/3, 1.667 times 2 or times 3. And that would be 5, for example. So these are some common ones in addition to a half that you may encounter. Now, there are other ones as well. A tenth. If it was 0.1, you'd multiply by 10. If it was 0.2, you multiply by 5. So, but the ones I've shown you are the more common ones, like a half, a quarter, and a third. So here we have this compound. It contains 40.9% carbon, 4.58% hydrogen, and 54.5% oxygen. Calculate the empirical formula for this compound. So the first thing we want to do is we assume a 100-gram sample. And you can assume any gram sample you want, but 100 is just the most convenient, because now that we have a 100-gram sample, we can find the mass of each element. So we found the mass of carbon, the mass of hydrogen, and the mass of oxygen. Now, using the molar masses, we're going to find the moles of each. So again, the molar mass of carbon is 12, hydrogen 1, and oxygen 16. So now we get our ratio, or excuse me, our moles of elements. So again, mass divided by the molar mass gives us the moles of each element. And now you'll notice here that carbon and oxygen have the fewest number of moles. So we're going to divide everything by 3.41. And you notice here that when we do that, we see that we get carbon's a ratio of 1, hydrogen is 1.343, and oxygen is 1. So obviously hydrogen is not a whole number, so we have to multiply something by 1.343 to give us a whole number. And so 1.343 is very close to 1.3333. So we're going to multiply all of these by 3. So again, we divide by the smallest number of moles. It gives us this ratio here. So we're going to multiply everything by 3 to give us whole numbers. Now you see 1.343 times 3 is approximately 4. It's 4.03, but you can round it to 4. So now we have the whole numbers. We can write the formula. And again, the order that the elements are given to us is given to us as carbon, hydrogen, oxygen. So you should write the formula as carbon, hydrogen, oxygen. Because if you write it in a different order, it's going to count it wrong, because this is the order in which the elements should be written. So the empirical formula is C3H4O3. So the only difference between this one and the last two examples was that it gave us the percent of each element instead of the mass. And so we have to assume a 100-gram sample, then divide by the molar mass of each element to get the moles, divide by the smallest number of moles to get the ratio. In this case, one of them was not a whole number, 1.343. So we multiply it by 3 in order to get the whole number ratio. So I wanted to get to molecular formulas. So with molecular formulas, we're showing you the actual number of atoms in the formula or compound. And so with molecular formulas, we just add one step to the end of when we're solving for empirical formulas. And again, there's different ways you can solve for molecular formulas. I'm going to show you one way, but if you do it a different way and get the same answer, no problem. But for us, what we're going to do is to find the molecular formula. We're going to first find the empirical formula and then multiply it by some number called n. And n is most of the time a whole number, but sometimes it could be a decimal form. But most of the time it's a whole number. And the way we get this n, or this ratio, is by taking the molar mass of the molecular formula and dividing it by the molar mass of the empirical. Now, the molar mass of the molecular formula is always given to you somewhere in the problem. You don't have to calculate the molar mass of the molecular formula. So when you're reading the problem, in the problem somewhere, it'll give you this number. Now, the molar mass of the empirical formula, you have to calculate once you determine the empirical formula of your compound. So for example, benzene has a molecular mass of 78 grams per mole. The empirical formula is CH. And so the CH has a molar mass of 13. So 12 plus 1 gives us 13. So this is the molar mass of the empirical formula. This is the molar mass. 78 is the molar mass of the molecular formula. So we divide the two to get the ratio, and it's 6. And so all you do is you take that number and you multiply it by the empirical formula. And so we get C6H6. So we're doing the exact same steps as empirical formula, just one step after that, we got to determine the ratio in order to multiply by the empirical formula to get the molecular formula. And sometimes this n can be 1. So sometimes a molecular formula can be the same as the empirical formula. So it can be 1 sometimes. So here we have a compound that, that's empirical. So here we have a compound that contains 2.47 grams of carbon, 0.342 grams of hydrogen, and 2.19 grams of oxygen. It tells us the molar mass of this compound is 146 grams per mole. What's its molecular formula? So again, this 146 grams per mole, this is the molar mass of the molecular formula. So we're not going to use this just yet. And we want to determine the molecular formula. So the first thing we have to do is take the masses of each element and determine the empirical formula. So step 1 is we find the moles of each element. And try not to round too much when you're calculating the moles. I would keep 3 or 4 significant figures, because if you round too much, it will cause error in your ratio. So the first step, what we're doing is we're determining the moles of each element. So now we have the moles of each element. We're going to divide by the smallest number to get the ratio. So here the smallest number is oxygen. So we're going to divide everything by the moles of oxygen to get the ratios. And so you see here we get a ratio of 1.5, 2.498. That's approximately 2.5. And we get 1. So you see here 1.5 and 2.5 are not whole numbers, so we need to multiply by 2 in order to get the whole number ratio. So again, 2.498 you can round to 2.50. So we're going to multiply each one by 2. And you got to make sure to multiply oxygen by 2 as well. So the empirical formula C3H5O2. And so we find its molar mass of empirical formula would be 3 times 12, 5 times 1 plus 2 times 16. So you take the number of each element, multiply by its molar mass, and you get the empirical form, molar mass of the empirical form. So now we have the molar mass of the empirical formula. We get the ratio by taking that mass and dividing it, the molar mass of the molecular formula by the molar mass of the empirical. 6. And so we get an N of 2. Yes, so again, we multiply everything by 2 to make them whole numbers, because you can't have decimals in formulas. So then we found the empirical formula, we found the molar mass of the empirical formula. We take the molar mass of the molecular formula that was given to us in the problem, 146 divided by 73 gives us 2. But then we multiply the empirical formula by 2. So we get C6H10O4. You can use whatever molar mass you like. I mean, 16 and 15.9999. You're not going to have much of a difference in the answer. But sure. And so the molecular formula is C6H10O4. So again, when we're looking for molecular formula, we have to first determine the empirical formula so we can get the molar mass of the empirical formula. And then we can find the ratio and find the molecular formula. So here we have an organic compound. Contains 2.79 grams of carbon, 0.35 grams of hydrogen, and 1.86 grams of oxygen. So they did this mass analysis. They got the mass of each element. They determined that the molar mass of the molecular formula is 129 grams per mole. We want to determine the molecular formula. So again, the first step, we want to convert mass to moles. So we're going to take the mass of each element and convert them to moles of each element. So mass divided by molar mass gives us moles. So we found the moles of each element. So now we'll notice that here oxygen has the fewest number of moles. So to find the ratio, we're going to divide each one by the moles of oxygen. And so we get a ratio of 2 to 3.01 to 1. And 3.01 is close enough to 3 that you can round this to 3. So we have 2 to 3 to 1. So those are whole numbers. So we can just write it as the empirical formula. So the empirical formula is, and again, you have to write it in the order that is giving you the elements unless it specifies a particular order. So since it gave us carbon, hydrogen, and oxygen, we're going to put carbon, hydrogen, and oxygen. And so to get the molar mass of the empirical formula, it's 2 times 12, 1 times 3 times 1 times 16. And we get 43 grams per mole. So that's the molar mass of the empirical formula. Now we're going to take and find our N. Well, now is when we use the molar mass of the molecular formula divided by the empirical formula gives us the ratio. And we get 3. So we have to multiply the empirical formula by 3 to get the molecular formula. So we get C6H9O3, and this again is the molecular formula. And so just to kind of summarize, when we're looking for molecular formula, we do the exact same steps we do for empirical formula, except at the end, we calculate this new component called N, which is the ratio between the molar masses of the molecular formula, which is given to you in the problem, and the molar mass of the empirical formula, which is something you calculate once you determine the empirical formula. Once you find this ratio, you multiply by the empirical formula to get the molecular formula. Also to keep in mind is that the order of the elements listed in the problem is the way you should write the elements in the formula. So since it gave us CH and O, we write it as CH and O. And that's all for this lecture. Until next time.